nondeterministic quantum communication complexity.
Right. Hi everyone. My name is Zuiddam, and this talk is about non-deterministic quantum communication complexity, and is based on joint work with Harry Burman and Matthias Cristano. So let me begin with defining a communication model, first classically. So we have three players, Alice, Bob, and Charlie, and they're given a Boolean function on three inputs. And each of the players gets one of the inputs, and together they want to compute the function value. Now, in order to do this, they are allowed to communicate by broadcasting bits. And they do this in rounds. So each round, one player broadcasts one bit. To make this model quantum, I replace bits by qubits as follows. So now a player is allowed to communicate by preparing a 3-qubit state of the form alpha ket 000 plus beta ket 111. So this is a superposition over classical broadcasts. And then the player will share this state with the other players. That's a quantum broadcast. Okay. And now, then also, of course, they are allowed to do any quantum local operations. Now I define NQ of F, the non-deterministic quantum communication complexity, as the minimum number of broadcasts that the players have to do to compute the function F non-deterministically. And what I mean by this is that if f of xyz equals 0, then all the players should output 0. Okay? And if f of xyz equals 1, then with some non-zero probability, all the players should output 1. Yeah, so it's like there's like a one-sided error, and this probability can be arbitrarily small, but it's non-zero. Okay, so this is the model that I'm going to be using in the rest of the talk. So let's give the main result. So what we do is we encode the function f in a hypermatrix by writing down all the function values for all the possible input triples. Yeah, so what you get is, so you can think of it as a big cube filled with zeros and ones. And the main theorem is that NQ of f equals the logarithm of the support rank of this hypermatrix, which I call ket of f, up to some small technicalities. Now, what's this support rank? So we define the support of any hypermatrix phi as the set of all coefficients, set of all coordinates which have a non-zero coefficient. Yeah? And then I define the rank of a hypermatrix as the minimum number R, such that I can write my hypermatrix as a sum of R simple tensors. And a simple tensor is just an outer product of 3 vectors. Okay, and then the support rank of ket f is the minimum rank of any tensor, any hypermatrix, complex hypermatrix, which has the same support as ket f. So this is, you can also say the support rank is the minimum rank that you can obtain by changing the ones in the hypermatrix into any other complex numbers. Okay, so let's give some examples. An easy example for 2 players is the equality function. So here we take the input sets to be the same, n of size 2 to the n. And the players, well, they have to decide non-deterministically whether their inputs are equal. So the hypermatrix that corresponds to this problem is just the identity matrix. And any matrix with the same support will have full rank. Yeah, so the NQ of this problem is little n. Another easy example for two parties is the non-equality problem. So the players have to decide non-deterministically whether their inputs are not equal. The matrix corresponding to this problem is the complement of the identity matrix. But now there's something interesting, namely this matrix has the same support as the difference of these two matrices on the right. And both of them have actually rank 1. Yeah, so this means that the support rank of this guy on the left is actually 2. Yeah, so the NQ of this problem equals 1. So these are just two simple examples. So let's go to an interesting family of problems. This is the family of problems that I want to look at in the rest of the talk. It's called graph-wise equality. Any graph defines such a problem. So you take a graph, every vertex of the graph corresponds to a player, and every edge of the graph corresponds to an equality problem that the players have to solve non-deterministically. Okay, so let's do an example on the triangle. We take the triangle graph. Each player gets 2 inputs, and the players are playing this equality game on the edges. So this means that they have to non-deterministically compute the function, which is 1, if x2 equals y1, y2 equals z1, and z2 equals x1. Okay. Now, what can we say about the NQ of this problem? So the trivial protocol that the players can do goes as follows, namely Alice just broadcasts x1, Bob broadcasts y1, and Charlie broadcasts z1. So this uses 3n broadcasts, so the NQ, and then they can easily compute the function. So the NQ is at most 3n. For the lower bound, note that we can group 2 players into 1 player, and then we obtain a 2-player equality game on 2n bits. So this means that the NQ is at least 2n. So what is it? Is it 3n? Is it 2n? Is it in between? So to study this question, I want to define a graph parameter. It's called the support rank exponent of a graph. And it's defined as follows. You take the non-deterministic communication complexity, NQ, of the equality problem on the graph. You divide it by n, and then you let n go to infinity. This is one way to study this number, to study where it is between 2n and 3n. And note that by our theorem, this expression is the same as the limit of n to infinity of the log of the support rank of the corresponding hypermatrix. So the main question now is that I want to study: what is omega s of G? What is this support rank exponent? And to attack this problem, we make a connection with algebraic complexity theory. Namely, it turns out that the complexity of triangular equality is tightly related to the computational complexity of matrix multiplication. And to study matrix multiplication, many tools have been developed. For example, there's Strassen's laser method and Young flattenings. So what we did is we generalized all these tools to study graph-wise equality. So let's look at some details. So the triangular equality, if you look at the hypermatrix corresponding to it, it looks like this. It's a sum over ijk of ket ij, ket jk, ket ki. And remember that we are interested in looking at this expression here, which has the support rank in it. So the matrix multiplication people, what they're interested in is the same expression, but then with the rank, with support rank replaced by rank.
You have 1 minute.
Yeah. Now, if we look at, so in the literature, it's known that this omega s is upper bounded by omega, and is upper bounded by 2.37. That's the best bound we have on this matrix multiplication exponent. And moreover, there is another bound here, which says that omega is at most 3/2 times omega s minus 1. Now, for us, this implies the following, namely that omega s of the triangle is between 2 and 2.37. And if omega s of the triangle equals 2, then omega equals 2. So you can say two things now. You can say, okay, if for the optimist you can construct, if you construct a good protocol for triangular equality, then you can get good matrix multiplication algorithms. And the other way around, you could also say, okay, this means that getting good protocols for triangular equality is very hard. Now, what we did is we looked at cyclic equality. So we were able to generalize Strassner's laser method to get non-trivial upper bounds on cyclic equality. And something else we could do is we could prove, using our theorem, that's a different direction, a so-called log rank conjecture in the message passing variant of this model, this communication. Here's a short summary and some further work. So I want to mention that in some further work we got better bounds on the cycle graphs, and we also got some bounds on complete graphs. Thanks.
Quantum techniques could actually be used to tell us something about matrix multiplication?
Yeah, so we haven't been able to do that, but that would be a very interesting thing to try. Yeah, so that would be a very fascinating thing to do. Yeah, but I don't know how to do that.